X. And similarly, if we say, Armenia, that thing is just a symbolic expression of the same type as any of these other symbolic expressions. And the fact that everything is represented in this uniform way lets us do some very powerful things. So, for example, let's say we iterate a function. We say nest the function f lots of times. We can have anything there. We could say, let's say, nest, put a frame around something, so then we'll get something like this. Or we could say nest, let's say, let's do this. Let's say nest, blur the current image that we get 10 times. And so what we'll see there is that successively it will get blurrier and blurrier. So this operation, for example, nest list, is something that's completely general across all the different kinds of objects that exist in the system. So this notion of symbolic computation is very important for being able to build a big system like this. There are a couple of other things that are important too. One of them is we want the system to kind of be as unified as possible, so that all the different pieces of the system, and it's a very big system, fit together perfectly. And that's important because it allows us to have, if we're doing computational geometry over here, and we're doing graph theory over here, and we're doing geographic computation over here, we can connect all those pieces together. One thing that's been important to us internally is that when you build an algorithm today, the typical best algorithm for something is an algorithm that makes use of methods that come from many different fields. So even though you think you're doing an algorithm that's just about numbers, that algorithm may very well use algebraic computation, it may use graph computation, may use all sorts of different kinds of things. And it's only because we have all those different kinds of things that we're able to create these more sophisticated algorithms. Well, as I mentioned, one of the big features of this language is that it tries to automate things. So one of the points about that is we just want to be able to say, as humans, do this operation. We just want to say, lay out this graph, for example. And then the idea is for the language to automate that process as much as possible. So there might be 100 different algorithms for laying out graphs, but we'll try and pick the best one for that particular graph, so that you as a human don't have to do that. Well, there are lots of areas where we're automating things, like, for example, we can automate constructing interfaces. And this is also a good example of symbolic stuff. So, for example, I could make all these sliders and they'll work. I could create some interface that is, I could use, let's try doing this. Let's try saying nest, a tab view. Let's see how this works. I'm going to, let's see whether this will work. Let's try that. Okay, that's cool. So this will make an interface that's a nested interface here that we could use to control the program. Well, another big thing that we've been doing is to try to automate deploying how the kind of deploying things from this language. So let me show you something. So let's say we want to create a website. Let's say we want to create a very simple website that just says hello. Okay. All I have to do here is to say deploy to the cloud that thing hello. And then what's going to happen is it will create a website, not a very exciting website, it will create a website that just says hello. Let's make it more sophisticated. Let's say we want to create a website that has, is going to make a picture of the word hello on a black background, on a yellow background, and we want it to be in 100-point font. And now we're going to say, and we want it to be displayed as a PNG. Okay? So now we'll say deploy that to the cloud, and then we should get something here where we just created, we created that thing which says hello with a yellow background. Or let's just for fun, let's say rotate that by actually let's do something really outrageous. let us do the following. Let's say, I have to remember how to do this. Let's say, what's the position of the sun? Okay, so let's say, rotate this thing by the current position first of sun position, by the current position of the sun. Okay? So now we do that, and we'll get a website, and then we go there. Oops, okay, it says rotate that. Oh, that's interesting. So it just says there, rotate by that. That's interesting. Now, why would that not be working? Let's see. Oh, I think the problem is, and that's an interesting problem, yes. The problem is that it doesn't know. Okay. I have to do something here, which I shouldn't have to do, actually. I have to turn this from a... yeah, this is something that should work. This should work. This is a... I should remember this thing. So let's try that now. I think this will now work. Yeah, there we go. So that's now been tipped to the angle of the sun. Let's say that instead of just wanting to make a fixed website, we want to make this be a form where we're going to say, let's make this be a form where we give it, let's say, well, let's just for a start, I'll tell you what, let's just give it. Just try something here. Let's try giving this the time of day. No, let's just give it an angle to rotate around. Okay, so let's say angle, and say that's going to be a number, and then let's say rotate this by that number, whatever that is, and then let's make this size be something variable. So let's say we've got an angle, and we've got a size, and both of those are numbers, and now, let's see, here we want to say that, okay, now we want to tell it, okay, I think this is right. So now we're going to try and deploy something which is going to create a form, I hope. There we go. So now we have a form which asks us the angle, let's say 44 degrees, and the size, let's say 200. Okay, so when we submit this form, we'll then get that at that size. Okay? So what we basically just did was to create a little website that I could tell it to just publish this publicly on the web. So then you've got a little website that does this computation. And when we do every time we submit something, it'll go back to our cloud, do the computation, send the result back. We could make it, if you're into sort of computer sciencey kinds of things, we could make an API out of this. We just have to change this form function to an API function. And now what we'll get is something where when we fill into the URL up here, we fill in, yeah, okay, so it needs to have two parameters. So it needs to have question mark, angle equals, let's say, 70, ampersand, size equals 150, for example. And now that's an API that can be called by any other program that does this computation. So again, if you're into computer sciencey kinds of things, let me show you something else that you can do. You can take that API function and you can have it, let's do this, and now we can say embed code of that, Java. And what that will do is to generate some Java code that you could put into a Java program that will call that API in our cloud. So if you're writing a piece of Java code and you suddenly say, I need to do something which makes use of kind of algorithms and knowledge in the Wolfram language, you just write the piece of Wolfram language code, and this will then give you what you need to knit that into the Java program. So okay, so then, well, lots of different kinds of things are possible here. I should say what I've been doing right now is to use the Wolfram language on a desktop version of it. There's also soon to come out a pure cloud version. And so what you can do there is, and this is going to be available in just a couple of weeks, you can use, for example, our programming cloud, and if I go here, I'll get the exact same computation abilities, but now this is just a web browser that's running here, and all the computations are running in our cloud. So, for example, I could go ahead and say, I don't know, let's make a nice picture. Let's go here. I have to look at the documentation to know how to do this. Let's make, let's say something like this. Let's go ahead and do the computation here. Go here, and now we'll do this computation, and this will all happen in our cloud in this web browser. And now we're able to pick that up and rotate it around and so on here. So everything that you could do on the desktop, you can also do just through a web browser on the cloud. And you can go from the cloud and you can write programs in the cloud and then deploy them to create websites and things like that. So I think this is actually going to be something pretty exciting because this language that we have has many important attributes. It basically automates a large part of the process of writing code, writing programs. And that means that a much broader range of people can write sophisticated programs. And that means, for example, that I think there's going to be kind of a wave of algorithm-based startup companies that are taking algorithm ideas and using our language to deploy those ideas into products. It's also a language that's very interesting for education because it's a language where you can start learning real things very quickly, and you can actually do computations that immediately relate to things in the real world. And so we're going to be doing a lot in trying to develop a programming lab for students to be able to use this language. So anyway, that's there are many different things that are happening with this language. So, for example, another direction is using this language to connect to devices and the Internet of Things. So this is a website that we put together, which is kind of an inventory of different kinds of devices that you can connect to. And so this is, and these devices measure all kinds of different things, from electric current to blood oxygen saturation and so on. The idea in our language is to be able to connect to all these kinds of devices. And as Bruce mentioned, the language is actually, a preliminary version of the language is actually bundled on the Raspberry Pi computer, which is a type of computer that you can use to connect very easily to sensors and so on. Okay, so that's some of what we're doing right now. Maybe I should tell you the story of how all this stuff happened. So, way back, long ago, I grew up in England, and I got interested in science pretty early in life. And so by the time I was a mid-teenager, I was doing physics research and publishing papers and things about particle physics, actually. So one of the things that was necessary in doing physics research was to do sort of mathematical calculations. And I, as a human, was not particularly good at doing mathematical calculations. But it so happened that I had learnt quite a bit about using computers. In those days, computers meant these giant things that you program with paper tape and all kinds of stuff like that. But in any case, at some point I started to ask, all of these mathematical calculations that I have to do for physics seem very mechanical. Why can't I just make a computer do these for me? Well, at that time there was starting to be some experimental computer systems that could do things like algebraic computation. And I quickly became, I guess, the world's largest user of such systems. Then realized that the systems that existed were kind of accommodate the kinds of computations I wanted to do. So back in 1979, actually, I was 19 years old, maybe just 20 years old. I said, you know, I need a better system for doing mathematical calculation than exists in the world today. And so after I tried to persuade other people to build such a system unsuccessfully, I said, okay, so now I have to build this myself. And I knew a fair amount about computers at that time, but I decided, you know, I should learn whatever was known about computer science. And I remember going to the Caltech bookstore and just buying all the books on the shelf about computer science, which was only about that many books, and, you know, reading through all these books and deciding that, yes, I knew a decent amount about what was known in computer science at that time. And so I started designing a language to do mathematical computation. And one of the things that I wanted to do was to say, to think about designing a language the same way as I thought about doing physics, which was sort of, there's all these phenomena about programs people want to write, and then let's try and drill down, let's try and find the fundamental building blocks of these programs, just like we want to find the fundamental building blocks of matter, for example, in physics. And so I ended up inventing a lot of stuff about symbolic programming and the kind of this idea of symbolic programming. And I built my first computer system called SMP, which was really focused on mathematical computation at that time. Then, well, by that point I was a professor type, but I kind of realized that this thing I built was pretty useful, not just to me. I was sort of its first target market, but also to a lot of other people. And so I realized that what I had to do was to start a company around this thing that I built. At that time, that was a little bit of a difficult thing to do because universities weren't used to professors starting companies. But and I also kind of had the idea that I didn't really know much about business. So to start this company, I would, you know, hire a CEO and so on, and I would try and build the technology, and I would have other people figure out the business side of it. Well, I ended up, that was a very useful learning experience, and that company eventually it went public, and it did all those kinds of good things. But it was, for me, it was a quite unsatisfying experience because it turned out that I discovered that I knew more about business than I thought I did, and you know, I kind of had a different vision for what should happen. So anyway, so but the result of that company was that I had a nice tool to use myself, this SMP system, to do research and so on. And so I went back at that time to doing basic research, and I ended up becoming interested in a very general kind of question that I'll tell you about. But just in terms of the sort of the flow of my life and the kind of the story of it, I ended up doing basic research for a few years and sort of tried to start building a field of science around sort of complexity and how complexity arises in nature. Then I kind of got frustrated with how slow it was to actually create a new field of science in the world and to get, you know, government funding agencies to fund it and all those kinds of things. So I decided to kind of go back to a plan B for myself, which was, okay, I need to build good tools for doing this science, and I need to build a good environment for me to be in, and I'll just do that myself, so to speak. And so I ended up starting my company, Wolfram Research. This was in 1986 or so, and starting to build Mathematica, and my goal with Mathematica was to build a system that would do sort of all the computations that I'd ever want to do in my life. So after first couple of years, and in that company, I decided I'm just going to be the CEO. I'm not going to hire somebody else to do that. I'm going to run the thing, and that's what I've been doing for the past 26 years or so. And the company has grown now to have about 700 employees, and the product Mathematica that we built celebrated its 25th anniversary last year, and it's now used in most R&D organizations around the world, and it's used in the US, for example. About 90% of the universities there have site licenses for Mathematica, so it can be used by everybody at the university. So it's been a quite successful thing. Then, but one of the things when I first built Mathematica, one of the things that I wanted to do was to use it myself to do basic science. And so let me explain a little bit about the science that I was interested in doing. So kind of, if you look at science today, sort of one of the biggest ideas in the history of science is probably this idea that we can use mathematics to model the natural world. That was kind of an idea from about 300 years ago that people like Newton and so on were big on doing. And so what I was interested in is, can we generalize that idea? There are some systems where that idea works very well, but what about all the places which seem sort of too complex to be represented by mathematics? What can we do in those systems? So I got interested in, can we generalize the sort of the basic idea of having a formal description of a natural system? And I realized that one can have rules that are sort of more general than the rules that exist in mathematics, and computer programs provide a good source of those rules. So then I got interested in the question of, if you just look at all possible computer programs, what do they typically do? So you can start looking at, let's say, some very simple computer programs, and there's a particular kind of simple program called the cellular automaton that I studied a lot, and here's an example of one of them. This is one where it's just a row of black and white cells, and there's a rule that says at every step what color each particular cell should become. So here we just start off from one black cell, we use that rule at the bottom, we generate this pattern. Now the question is, what happens if you change the rules? So if you change it just a little bit, very simple rule, very simple behavior. Change it again, you don't get quite such simple behavior. If you continue running this, you'll get a pattern like that. It's a very intricate pattern, but it's still in a sense very regular. And you might say, okay, anytime I use a simple rule, I'm always going to get a very regular pattern of behavior. But okay, then you can sort of think, let's use a computer kind of like a telescope and look out into this computational universe of possible programs and see what's out there. Well, you can just like enumerate all possible programs. Here's the first 64 of those programs, and you see some of the programs behave in very simple ways, but some of them behave in more complicated ways. And my big favorite is Rule 30, and this is what it does. It has that rule at the bottom. It starts off from just one black cell at the top, but it does something that gets quite complicated. In fact, if you continue it longer, you'll see that it looks really quite messy and random. There's some regularity you can see on the left, but like if you look at the center column of cells in this pattern, they seem for all practical purposes random. So even though there's a very simple rule at the bottom, the behavior you get is for all practical purposes random. Well, I think this is a big deal because when we're not used to this, our intuition says if you want to make something complicated and random, you have to have very complicated rules. Let me show you another example. So here's another case. Again, the rules are very, very simple, but the behavior is very complicated. And I think this is something that is sort of a big discovery that sort of points the direction to sort of a new kind of science that one can do that's based on studying the computational universe of possible programs. So you can study this in lots of different places. So for example, let's say you're studying, let's say, the growth of snowflakes. It turns out you can make a very simple model that just uses a rule just like these kinds of rules I just showed, and does a very good job of reproducing the actual behavior of snowflakes. Another case I've studied a lot, that in fact Bruce here has also been much involved in, is fluid turbulence, studying the complex flows and fluids. And one of the big things that Bruce mentioned earlier, that Bruce has much been involved in, is finding out ways in which one can use very simple cellular automaton rules as a way to sort of mimic underlying molecular behavior and reproduce the behavior of fluids. Do the same kind of thing in biology. I've been interested in things like how do pigment patterns on mollusk shells arise. It turns out that, again, these cellular automata do a very good job of explaining how these patterns arise and how you can get complicated patterns as well as simple patterns. Well, there are lots of different places where this kind of thing shows up. From a sort of more theoretical point of view, you can ask, okay, so why is there complexity in a situation like this? And there's a thing I call the principle of computational equivalence, which explains that. The way that you think about